Good afternoon. First of all, I would like to thank very much the Geomorphological Union of Brazil for having invited me to join you for the 13th Sinageo conference. I know that these events are very well attended and by numerous geomorphologists, both early career and medium to senior career geomorphologists. So I'm really very happy to share with me the outputs of research that we have carried out with respect to coastal landslide as a geohazard and the contribution of geomorphological research to that very important topic. A very important topic, especially in the frame of climate change and considering the issues of sustainable development that geomorphologists have to tackle nowadays. Well, this is also a story of research that started as a curiosity-driven research, and that from time to time in the last 15 years was able to collect some funding by European institutions, and that was also able to attract the interest of local institutions and stakeholders. The content of my talk will be related to rocky coasts as a source of hazard, and I will let you know about the Mediterranean context that may not be familiar to some of you. And then I will focus on the Maltese Islands, which are located really at the center of the Mediterranean Sea. And I will show you our research focused on the recognition, mapping, and monitoring of coastal landslides, how we discovered and mapped submarine hidden landslides, and how we were able to provide some chronological constraints to the long-term coastal evolution of the Maltese coasts, with special reference to the dating of landslides. Then at the end of the talk, I would like to show you how important it is to integrate terrestrial and marine datasets when you have to deal with coastal geohazards and georisks. So, rocky coasts are of course a source of hazard when you have to deal with rocky cliffs that could be eroded at their base by sea action. Despite the intensity of the sea action, of course, you may have landslides of different types, mainly rock falls and rock topples. But I will show you that around the Maltese Islands, coastal erosion causes also other types of landslide that sometimes are really spectacular and may involve different hazards. So, in the Mediterranean context, not only you have hazard conditions like you have in many other, along many other coastlines of the world, but at the same time you have a quite significant vulnerability related to the wide and continued attendance of coastal areas from visitors, tourists, and local inhabitants. We have to say that in the frame of global and particularly climate change, the frequency and intensity of extreme events has increased, and this has often led to an increased coastal risk. On the media, of course, you can find wide information about different type of coastal cliff instabilities. I am showing you a few of them in the Mediterranean Sea, starting from this very significant case of a very famous and highly attended beach in the island of Zakynthos in western Greece. This is called the Shipwreck Beach that can be reached only by boat and where there is a sunk shipwreck. So many visitors go there to enjoy both the beach and the sea around. And the 3 people were injured due to a rock fall back in 2018. I have reported here the link to the video. If you would like to see it, I suggest the vision, because it shows those who are not familiar with coastal cliff instability what this could mean, especially if you have tourists around. And then you will see also that this landslide, this rockfall, caused a little tsunami in the bay. I would like to mention also another significant case which caused the death of two young ladies on a school trip. This happened in 2010 on an island outside Latium near the coast of Rome, where a very small landslide, but a lethal one, detached from a cliff. So this shows the unpredictability, the degree of unpredictability of these kind of landslides, and that also small detachment can cause the death of people. And this landslide occurred in April. If it had happened during the summer period, probably the number of victims would have been much higher. Other cases all around the coast of the Mediterranean can be found. I have reported here another link if you would like to see this rockfall taken by an amateur video maker. Of course, the area, as you can see, was kind of dangerous, and it was restricted its access. But nevertheless, some people were around, and when you have landslides like those, of course, you can have also tsunamis as an induced effect. And so also those who are not on the beach but on the boats nearby can suffer from the effects of these landslides. A very striking event occurred in Liguria, northern Italy, along its very famous coast, a coast that is attended by thousands and thousands of tourists every year, during the whole year actually. And here we are at the village of Camogli, where a cliff, a portion of a cliff, detached. Due to this event, a large part of the cemetery of the village collapsed into the sea. And very dramatic scenes were filmed, and here you can find a relevant video where you will see the collapse of all the structure. As you see, these areas are very highly inhabited, so the degree of vulnerability is quite high, and when you have such cliff, of course, hazard, landslide hazard is high as well. So by the combination of geohazard and vulnerability, of course, you can get a high risk for population, structures, and infrastructures. I mentioned to you that I was going to focus on the Maltese Islands, where the same problem is actually affecting the coastlines. In 1970, a 12-year-old boy was killed by a rockfall along the northwest coast of Malta, which is actually the area on which we've mostly focused our attention. But injuries are reported practically every year, because collapses like those related to coastal cliff erosion by sea action occur, or, as you can see on the right, where you have detachments of rock blocks near the coast affecting footpaths. Here there are a network of footpaths that is used also to reach scenic places where you can have nice views, and tourists could be in danger, also due to very small detachments. Sometimes detachments from higher cliffs can reach the beach, which is actually at the bottom of this red dotted line, and potentially be dangerous for tourists on the beach itself. Sometimes collapses along the coast may also endanger geoheritage, and this is the case of the disappearance of an icon of the Maltese landscape, the so-called Azure Window. This is an arch that has been considered the most topical, the most iconic location in Malta, and that was used by any tourist dealers in Malta as a symbol of the islands. Actually, part of the cliff collapsed back in 2012, making the window larger. At that time, local institutions were worried about the possible collapse of the roof of this arch, and so they restricted the attendance of this part of the plateau, where actually the rock is quite resistant. But what was not fully considered is that the sea action was undermining the stability of the portion of the arch located toward the sea. So the basement of this pillar was getting thinner and thinner due to wave cut at the base. So actually in March 2017 there was the full collapse during a storm surge, the collapse of the entire Azure Window, which now looks like this. So we have only the right part of what was the arch still standing there. There's of course had a quite remarkable emphasis on newspapers back in 2012 when the window was enlarged, as this newspaper was mentioning, and also afterwards. This case was not mentioned only in Maltese newspapers and media, but also all around the world. This is, I was mentioning that this is an area that the Azure Window can be considered as part of the geoheritage of the Maltese Islands, as well as the surrounding areas where you have paleosinkholes that are really exemplary cases of evolution of these karst landforms. So here we try to study this before the Azure Window collapsed and published a paper on bridging natural and cultural values of sites with outstanding scenery. The cultural values of this site reside also in the fact that this area was considered as of high value by the Maltese Knights, the Knights of Malta, who were also participating in the Crusades, who were running the island for quite a long time in historical periods. So you may have understood that the vulnerability at different levels, the vulnerability of the Maltese Islands, such as of other areas in the Mediterranean, is quite high. In particular, the northwest coast of Malta, which is characterized by a spectacular landscape, is attracting many visitors. Together with the visitor attending other parts of the islands, we have to say that 70% of the Maltese global domestic product comes from tourism, so a very significant part. And thus our intent was to try to start with basic geomorphological research and then go to applied geomorphological research to try to define landslide susceptibility, landslide hazard, and possibly landslide risk. And then we had to start from the recognition, mapping, and monitoring of coastal landslide. Being aware that coastal landslide in the Mediterranean are often overlooked, are often neglected, more emphasis being given to coastal erosion sensu stricto, I mean beach erosion, beach retreat, and so on, which sometimes takes place with more rapid changes than coastal landslides. The case study of Malta was considered by our research team as an open-air laboratory for the study of coastal landslide in the Mediterranean. There is a scarce vegetation, as you will see. The geology from this perspective is quite simple, with a subhorizontal stratification, with very clear evidence of faults, fractures, and joints. So all the elements that can lead scientists, and particularly geomorphologists, to focus on the processes of landslide, including the type of landslide, the mechanisms of such landslides, and so on. I would like to show this map of the Maltese Islands that you see are located in the central part of the Mediterranean Sea, south of the island of Sicily, which belongs to Italy. And this is the area on which we focused our attention, but we have studied also other areas of the islands. Here I would like to show you the increase of populations that occurred from 1970 to 2019. So actually from 300,000 in 1950, we got to 400,000 inhabitants in 2010, and now the population is well above 500,000. So you see that in about 50 years, the population increased by 200,000 people, which is extremely significant in terms of possible vulnerability. And at the same time, during the same period, and especially very recently, the population, the visitors, the tourists visiting Malta increased significantly, except the pandemic period, of course. So in order to well understand the problem of coastal landslides, we started from the beginning, trying to define the different types of coastal geomorphotypes, also trying to get information and map storm and wave deposits. So finally, with respect to our aim, or the aim of the talk that I'm giving today, we had to concentrate our attention on plunging cliffs, so vertical cliffs that we have especially in the southwestern part of Malta, on screes that we have in particular geological conditions that I will show you very soon, and in cliffs that occur somewhere along the island, cliffs that have beaches at their bottom. These are the type of cliffs and anyway of coasts that we concentrated our attention on. Plunging cliffs, for example, this is the typical cliff that you can find in limestones in southwestern Malta. These screes that you can see are related to the presence of a limestone cap over less resistant formations. Actually, these are blue clays, and then cliffs with beaches beneath. 35% of Malta's coastline consists of rocky coasts, possibly affected by the processes that I'm going to describe and that we have tried to study in detail in the frame of a series of projects funded by the Europa Major Azure Agreement. Actually, we got this funding after we started the project. After we started our research, we were able to convince the Council of Europe that it may have been of interest to start funded research on coastal landslide in the area. So we had a series of projects that accompanied us and enable us to buy instrumentation and to run the monitoring along the coast. I mentioned earlier that the geological situation as far as the landslide recognition and monitoring is concerned is quite simple. So we start from the bottom and we have lower coralline limestones, then we have other limestones called globigerina limestones, then we have blue clays, so this is a marley and clay formation, and then we have a very limited outcrop of a formation called green sand, quite a friable one, and above we have the upper coralline limestone plateau. This is one of the few spots of the islands of Malta where you can see the full succession, because in other parts of the islands, due to the presence of faults, you may either see a part of it, the lower part sometimes, and the higher parts in other stretches of the island. However, from here it is very clear that for coastal processes and landforms, the geological control in terms of more resistant and possibly fractured and jointed rocks, I'm referring to the limestones, and the blue clay that tend to have a viscoplastic behavior, especially if water is there, condition very much the evolution of the coast. This is a 3D model of the northwest coast, and I would like to point out this promontory about which we will talk later on, because actually it's a laboratory within the laboratory of the open air laboratory of Malta. Here you can clearly see the cap rock, which is the upper coralline limestone plateau, the blue clays beneath. Actually, the relative thickness of these two formations plays an important role in the development of landslides. Sometimes, in fact, the blue clays are very thick, like here with respect to the cap rock. Sometimes it is you can find the opposite situation. And of course, it is also very important to see whether the sea action whether the sea is acting and eroding the blue clay at the coastline, or if at the coastline you have other formations due to the tectonic displacements that I mentioned to you earlier. So this is what we call, Maltese call, Il Carraba Plateau, which was a much larger plateau that was then dissected, dismembered due to rock spreading and block slide phenomena that occurred for a long time. How long? I will try to show this later on when we will talk about chronological constraints of these processes. Since the beginning, we understood that it was very important to deal with a multi-technical and multidisciplinary approach to get to a proper landslide hazard assessment. So, as I said before, we started with traditional geomorphological surveys and produced geomorphological maps. And since the beginning, we had in our mind to find the right places, the right locations, the right samples to try to date these landslides. Finally, we realized that the only way to date them was to use the technique of cosmogenic ray exposure, having in the area, especially limestones, the CL36 was the only way to make this dating. And finally, you will see that we got some interesting dates. But before going to this, what are the monitoring techniques that we applied? So interferometric techniques, GPS ones, we used extensometers, fissumimeters, we used lidars, we used uncrewed aerial vehicles, that is drones, for our surveys. So the first, beside the recognition of landslide and types of landslide, one of our first objectives was to understand whether these landslides were active or not. Because looking at the images that you've seen before, you understand that there might have been quite a significant activity of landslide in the area. But now the climate is quite dry. The islands are characterized by a Mediterranean climate, and the input of water is not so significant. And so we were wondering whether these landslides were still active. And I will show you what we discovered. We also tried to show to understand what was the evolution using photogrammetry and using photos of different periods. We also asked support from geophysics for ground penetrating radar to understand how and to what extent the Coralline limestone plateaus were extended, and then also other geophysical investigation to detect other important parameters like through ERT. We also used permanent scatter interferometry combined with the method of weight of evidence, and this led us to get to landslide susceptibility mapping. So PSI combined with PS time enable us also to define the displacement trends. Geomorphological survey and mapping was finally aimed at mapping landforms, all type of landforms, but with, of course, special attention to landslides. Recognizing different type of landslide and their state of activity was fundamental, and these information were reported in the geomorphological maps. And we also wanted to understand the role of rock spreading and block sliding in the coastal evolution, since we understood from the beginning that this was one of the major issues that have to be considered. You can see here the edge of the plateau on the right of this photograph, and the big blocks that are detached, that are tilted, and that move over the clays and eventually reach the sea. When these big blocks reach the sea, they play an important role in armoring, in protecting the coastline from erosion. But where the clays are not protected by these blocks, of course, the sea action can play a major role in coastal erosion and coastal retreat, possibly triggering further or favoring further landsliding. So sometimes, as you have seen in the slide before, the clays reach the sea. Sometimes, due to tectonic displacements, you can have other type of rocks touching the sea, reaching the coastline. So every stretch of coast has to be studied in detail to understand this relationship between coastal action, sea action in terms of coastal erosion, and the possible response in terms of landslides. This was one of the first map that we produced, the map of the northwest coast. You see the promontory I showed you before here, and we depicted landslide with different symbols according to their type and with different colors according to their state of activity. And in fact, since the first installment of fissurimeters, and from the first measurements, GPS measurement, we realized that these large movements were active. Of course, these are slow-moving phenomena, but we realized since the beginning that they were active. We experimented this in specific places where rock spreading and block sliding was occurring. As you see from this graph, block slide actually represent 63% of the area affected by landslide on the northwest coast, and the rock spread 13%, so the two of them constitute most of the landslide types affecting the northwest coast of Malta. Actually, the presence of these two lithotypes, one over the other, that is the plateau of Upper Coralline limestone over the blue clays, clearly favors this type of phenomenon. When we deal with coastal landslide, and particularly with coastal hazard due to landslides, we have always to stress as geomorphologists that different types of slope instability, of cliff instability, can lead to different type of hazards and vulnerability. So we should not generalize when we talk about landslide hazard, not only on coastal areas, but of course also on hilly and mountain areas. And we have always to consider that distinguishing and recognizing different type of movements is very important. As well as important it is to understand the material, which is the material involved in the movement, and the possible volume and velocity of the material involved. So after the first tests that led us to understand that these phenomena that we were focusing on were active, we started interferometric analysis to get a wider picture of the possible coastal instability. And we realized that along other areas of northern Malta, there were situations where a certain instability characterized coastal cliffs. I'm referring to the orange and yellow dots in this image, which refer to active deformation. You see more in detail one of these areas along the northwest coast where you have clear evidence of instability. Instability which is not just inherited from the past, but which is occurring now. So this was the first evidence coming from localized GPS and monitoring and from the fissurimeters, and then more widely from interferometric analysis. Let's focus again on this promontory. You can see very clearly the different behavior of the material above, the Coralline limestone, and the material below, which is the blue clay. Here around you can see also a series of footpaths that bring many visitors all around the year to get around here. So since the beginning we understood that there is something alive below this cliff, and which is related to the expansion and the shrinking of the blue clays according to the presence of water penetrating during rainfall within the cracks and reaching the substratum, the blue clay substratum, making it more plastic, more ductile. This, of course, favors rock spreading with lateral extension of blocks that tend to tilt, that tend to slide over the clays. As I showed before, also in this case, the blocks are armoring the coast, giving a natural protection from coastal erosion, which does not occur here in the upper right part of the image, where you see that there is a quite significant coastal erosion and quite steep unvegetated blue clay deposits. So since the very first monitoring of these features, we understood that they were active. We understood that these movements were quite slow, but at the same time, we understood that this slow movement occurring large wide areas could cause what we call collateral movements. So if you have something alive, let me use this expression, something alive in terms of deformation below this plateau, then you may expect that beside very slow movements like these, you can have sudden rock falls and rock topples, which may endanger coastal visitors. We published some papers regarding these interferometric analysis, and also how we used the interferometric analysis to reach to a landslide susceptibility modeling of these processes. More recently, we also used drones to understand the type of movement, mechanics, and behavior of the high number of big blocks that surround the sites I've shown to you earlier, and also at the Carraba Plateau, where you see we have been monitoring and mapping a large series of blocks using drones. This is the same plateau seen from one of its flanks. This is a view from the north to the south. So you see that we have a limestone plateau of about 15 meters and below about 30 meters of blue clays. And here are the big blocks that detach from the front. Consider this image because it is from here that we took samples for cosmogenic ray exposure dating. It is significant what we collected in terms of movements. This is a scheme that would like to show both horizontal and vertical displacement at different benchmarks, the benchmarks that we put on the plateau and that we are monitoring by GPS measurements. So you see that, for example, this benchmark showed a movement of 6.6 centimeters in something like 13 years, so an average of about 0.5 of movement of this block toward the sea. But if we look at the image before, the year after it was 0.8, which means we are dealing with very slow movements, but sometimes look at what happens. This is the image of May 2018. This had moved for so many years, you would say just 1.2 centimeters, but look at this, the movement disappeared the year after. This means that this this block moved backward. So how can a block move backward? Actually, we are experiencing tilting here. So blocks sometimes move forward and sometimes move backward. And this leads to a continuous movement. So irrespective of the total displacement forward, it is important to detect how much they move backward and forward, because this is progressively opening cracks. This is progressively favoring the detachment of rock falls and rock topples. Here we do not have very significant vertical displacements that instead we have at another site. This is another site a few kilometers north of Il Caraba Plateau. This is called Angkor Bay, and on the side of the bay you see these large cracks. These large cracks have favored through time the displacement of large slabs of rocks, where these slabs of rocks of Coralline limestone are something like 12 to 15 meters thick, and here even much thicker. Here again we measured horizontal and vertical displacement, and as for the horizontal displacement, you see that in something like 14 years we had displacement of slightly less or slightly more than 1 centimeter per year. Again, we are talking about slow-moving landslides of rock spreading and block sliding type, but in terms of hazard and vulnerability, we have to consider that we have this village here beneath with a swimming pool, for example, and little huts. What is this? This is an amusement park. It's called Papaya Village, and actually it is the place where they filmed the film Papaya, a Disney film directed by Robert Altman, with starring Robin Williams. So quite an important film. And afterwards, the scenes of the film should have been removed, but this did not happen. And after a few years, the village was used as an amusement park. Actually, an amusement park in a suggestive place because it's full of rocks, full of pinnacles, cracks, and so on. But this is actually an active landslide. And besides these movements of these big blocks toward the coast that may endanger, not just because of this slow movement, but because of possible rock falls and rock topples, the little huts, the little structures of this village, which is attended by thousands of visitors every year. In the upper part, you see that we have also significant lowering. So here at benchmark 102, we had 15 centimeters of lowering, and at 103 we had 26 centimeters of lowering of this big slab of rock. This is actually to be considered in terms of geohazard and georisk, given the important vulnerability of the site. Now we have just we are publishing a paper. It was recently accepted on engineering geology, and if any of you is interested in looking at the combination between GNSS monitoring results and modeling results, we have to try to explain how this movement could occur with the formation of possible sliding surfaces beneath. As mentioned earlier, we reached also to the point of producing susceptibility maps by using data coming from the permanent scatter interferometry combined with the weight of evidence method. The parameters we considered were slope angle, curvature, distance from coastline of the cliffs I showed you before, the distance from the scarp, the faults, the joints, and the topographical position index. So through that, we were able to outline different susceptibility classes. And you see that some of these areas are characterized by high. This is the area of Papaya Village. This is the area of Plateau. They are characterized by high to very high susceptibility classes. Well, then we understood that it was important to devote our attention not only to what happens above the sea level. It was quite clear, even from Google Earth images or aerial photographs, that landslide occur also, or landslide deposits better, occur also below the sea level. So the question was, were these landslides occurring some time ago, moving from the cliffs down into the sea, or were these landslides occurring in different periods? For example, when the sea level was much lower than today, and just afterward rose up at the level it is today. So we really understood that we had to look below the sea level, with the aim then to integrate the terrestrial information we already got with the marine data sets that we were going to collect. Because it was quite clear that a deeper understanding of long-term coastal changes actually depends from this integration. And this integration is also beneficial for prediction of risk scenarios. So the Council of Europe, through the Europa Major Hazards Agreement, enable us to make a multi-beam survey through some funding, and we were able to collect a precise map of the seafloor. A precise map which is synthesized in this map that shows the coastline of the LGM, of the last glacial maximum, which for these areas is between 24,000 and 19,000 years BP. At that time, this was the situation. The Maltese Islands were not islands, but they were connected with Sicily. This is Italy, I mean the Italian peninsula, which was linked to Sicily. So the paleogeography was very different at that time. And you can see the difference between the coastline at that time and the coastline today. Here the promontory, here Papaya Village. And so we tried to map landslide deposits below the sea level. And we realized that actually the terrestrial deposits, so the deposits which outcrop above the sea level, are around 1/3 of the total deposits. So 2/3 below the sea level and 1/3 above the sea level. Here you see the spectacular detachments of rock blocks just over Papaya Village, which is down here. This is the detachment from this part, and the big crack that you can see on the B image is this one. So this is another view of 3D view of Angkor Bay, with the amusement park located here. And again, in this image of Angkor Bay, you see the coastline in blue here. Yeah, the rugged topography clearly indicates where these blocks occur. And you see from here how they are extended, to what extent they are outcropping below the sea level, quite significantly. So these deposits, also in other parts of the northern west coast of Malta, reach depths of about -40, -50 meters below the present sea level. Okay, so let's go back again to this cave. This one, but if you go and map also the deposit below, which was possible through this more detailed multi-beam survey and mapping, you get a very wide accumulation. So you can imagine how larger the Caraba Plateau had to be in the past. We also find Caraba plateaus submerged nearby the coast, which was also quite interesting. I have mentioned dates, chronological constraints, cosmogenic ray exposure dating, and we perform them, and they enable us to prove some of our hypotheses. This was the first time that these landslides were dated in Malta, and investigating the time of these possible first-time failures made it possible to understand also the possible situation, morphoclimatic situation when they were occurring. So again, look back at the situation of about 20,000 years BP during the last glacial maximum, when the sea was at -130 with respect to today. The situation was this. And at that time, these cliffs were far from the coast, of about 800 meters from 1 kilometer. So again, our question was, were these landslides occurring near the coast and prolonging into the water when they occurred, or were they occurring in a total terrestrial environment and then the sea covered part of the deposits during post-glacial sea level rise? And the dating were very useful in trying to answer this question. So we took sample at different cliffs. Cosmogenic ray exposure dating takes advantage of the fact that when you have a detachment and the surface is left free, the cosmogenic ray can hit the surface, and then from there they leave a trace that you can date after even after thousands of years. So, in collaboration with the University of Exeter and the National Australian University, we were able to date some landslides. And I have to say very frankly that we were positively surprised by the dates that we got. For example, because they were somehow proving our geomorphological hypothesis and interpretation of these landslides, which was actually that these landslides occurred when the sea level was much lower. In fact, at Papaya Village, we found a date of 21.4 years BP, when the sea level was 130 meters below the present level. And these deposits now go down to the sea to -40, -50. So this is a clear evidence that these were fully terrestrial landslides that have been partially submerged only later on when the sea level was rising. The same, sorry, this is Papaya Village, 21,000 here, this big scarp above the big slab. At Caraba Plateau, we had a date, the oldest date of 15,000 years BP. At that time, the sea level was about -110. And since again, these deposits can be found only, let's say, at a depth of -40, -50, this means that we were having also in this case a terrestrial landslide that was only after a few thousand years covered by water. So you see that these landslides reach -30, -50, -40, 50, and so when these landslides occurred, when the oldest landslide that we dated occurred, they were frankly terrestrial landslides. We realized with the dating, even if we do not have many datings, that first-time failures involved large portions of or the entire slope. And at the beginning, we thought that the situation was reverse, that the movement were progressing inland. But finally, I will show you how the geomorphological interpretation could be. But before, I would like to show again what was the depth of the water at -130 meters when this landslide event occurred, -110 when the event occurred at 15,000 years BP. Actually, when we add the other events of 9,000 years BP, 10,000 year BP, 7,000 year BP, there was an interaction. There was an interaction between the sea, whose level was increasing, and the landslide deposits. So it is possible that these events have been favored also by the action of the sea, but not the oldest movements. Here we were in a terrestrial environment. So the plateau evolution models can tell us something in terms of classical interpretation of such phenomena that would foresee a progressive detachment of blocks. So in that case, you may expect that the older detachment is closer to the edge of the cliff, and getting inland, you get more recent events. This actually was not the case of the dates that we found, because we found the oldest dates inland and more recent dates instead in front. This could be linked to a large scale failure of all this part, and then further dismembering in more recent times of the blocks. So this would justify the fact that you have the older free face cliffs inland and not toward the sea, which is actually here. So this information was quite important, even if it is in very long term, because it gave us information about the geomorphological evolution of the area. So on the one hand, we started understanding since the beginning that these phenomena were active. And then going back into the past, we understood the time frame in which these phenomena were active, and probably they were even active before. But at least we were able to study a time frame period of at least 20,000 years. Integrating the terrestrial datasets and the marine datasets, we were able to show how important this integration is. And we also made a review of existing papers in order to better address our research. And we realized that this integration is really important because it contributes to a more effective and sustainable coastal management, including risk reduction. While we were carrying out our research, we looked at different papers, and we tried to reconstruct and to provide schemes on how we can integrate techniques that are generally used onshore and techniques that can be used offshore. So we published this scheme in a recent paper on the journal Water, showing different technological solutions that enable to collect high-resolution terrestrial and marine data, which are very important for geohazard assessment, also when you deal with coastal landslides. We promoted a special issue of the journal Water dealing with the landscapes and landforms of terrestrial and marine areas, and especially we solicited papers dealing with the interface between terrestrial and marine areas. We collected 15 papers in this special issue, and we as editors worked on the editorial that we entitled 7 Good Reasons for Integrated Terrestrial and Marine Spatial Data Sets in Changing Environments, also taking into account global and climate change. We realized from our literature review that geohazard played a major role. So what we experienced on the field, what was also other colleagues all around the world experienced. And within this paper you can find a wide bibliography, though these kind of research are at an initial stage. So geohazard papers are 34.5% of all the papers that we were able to collect. And geohazard, of course, as we have seen, are very important. I mean, the study of in an integrated way, the study of terrestrial and marine data sets in an integrated way are very important for the assessment of coastal geohazard and vulnerability. The same applies to the late quaternary changes of coastal landscape, as we proved with the chronological constraints that we were able to give to our landslide. It's about 10% of the paper that deal with more longer terms and more more pure, let's say, papers that deal with pure landscape reconstructions, landscape evolution reconstructions. And then we have geomorphological mapping. About 8% of the papers deal with geomorphological mapping. So after this literature review, we tried to make our own map of landslides. So this is the map of the emerged and submerged landslide deposits along the northwest coast of Malta, where you see the minus 130 coastline of the LGM, and you see the present coastline here. The plateau, here is the amusement park. And we we mapped all the landslide deposits that you see are very well developed all around the coast. But we tried to do something more. We tried to map not only gravity-induced deposits and landforms, but also other types of deposits, including fluvial and torrential landforms, karst landforms, man-made landforms, and so on. And we published this map on the Journal of Maps in 2017, and you can see that we use different colors with the same symbol to indicate parts of the landslide, portions of the landslide that are above the sea level, and parts of the landslide which are below the sea level. Well, coming to some final remarks, what were the lessons that we learned during these years that we spent studying the Maltese coastlines? We understood that it is of paramount importance to deal with coastal geohazard working on geomorphological issues. So geomorphology, and this is what we have to stress all the time, especially to public institutions and stakeholders, that if you want to prevent or mitigate georisks, the geomorphological approach is very important. And coastal areas often host tourist and recreational activities that are exposed to geomorphological hazards and risks. Landslide mapping, monitoring, and also modeling proved to be the path to be followed for a correct hazard assessment and management. I've tried to show you that it is not enough to say that in an area we have landslides, generally speaking, but we have to identify, recognize the different type of landslides, because they would have different velocities, they will have different volumes involved, and so on. Terrestrial and submarine landscapes should not be investigated separately, which sometimes or often happens, because on the one hand you have marine geologists looking at what they find beneath sea level, and then you have maybe geomorphologists or geologists that look at what happens above the sea level. So for a correct land management, it is really important to integrate these studies and to integrate the data sets, because the interpretation and analysis of these data sets is really important, both for long-term geomorphological evolution understanding and also to achieve useful information for hazard and risk assessment. We are continuing our research in the Maltese Islands, and submarine geomorphological mapping is now being extended to areas to the east coast of Malta. We are dealing with coastal vulnerability assessment and mapping in the island of Gozo. We are also taking into account the potential impact of sea level rise in terms of areas possibly inundated in different time frames, considering especially the IPCC scenarios for 2050, for the 21st century. All this has attracted, as I mentioned earlier, the collaboration with the stakeholders, which for us is very important because it proves that geomorphology has also a very important potential in terms of applied geomorphology. The research perspectives, we would like to understand whether the vast landslide deposits which are below the sea level are actually moving or not. Is the ceiling of the water, is the cover of the water enough to keep them stable, and only the part above the sea level is moving, or are they moving as well? So now we are trying to explore possibility of monitoring what is happening below the sea level to these landslides. Then we would like also to find a way to produce vulnerability and risk maps that take into account aspects of climate change, so the long-term sea level change on the one hand, and the frequent meteorological events on the other end that can lead, for example, to storm waves, storm surges, and so on. And then from a practical viewpoint that can be of interest to local institutions, the definition of protocols that can be utilized not only in Malta but also in other coastal environments for risk reduction and resilience improvement. If you found the geomorphology of Malta interesting, I suggest you this book, The Landscape and Landform of the Maltese Islands, edited by two Maltese colleagues and friends. And this is one of the books of the series World Geomorphological Landscapes, edited by our colleague Piotr Migon, that you will surely know. A series that has the auspices of the International Association of Geomorphologists. Here you can find my email address if you would like to share any ideas, if you would like to send any comments related to our research. I would very welcome to receive it and to share it with the colleagues of mine who are working on these sites together with me. I would like finally to, as president of the IEG, to invite you to participate in the Coimbra International Conference on Geomorphology that will take place between 12 and 16 September 2022. You see that the theme of the conference is a topical one, geomorphology and global change. The conference is now expected to be in physical presence, but of course we are ready to manage it also in different ways, either mixed or online, in case the pandemic continues or gets worse. Anyhow, our wish is to have the chance after such a tough period of pandemic to meet all together, to enjoy a conference in physical presence, and to participate in field trips and in a quite interesting intensive course for young geomorphologists. So please have a look of the website of the International Conference on Geomorphology, and I hope to see you soon there.